Partial equilibria, part 1. In topic 1, we have 6 broad objectives. Firstly, we want to understand how partial equilibrium is reached. We then go on to solving partial equilibrium where we only have a single good model using linear equations. Then we solve for a 2 good model, again using linear equations. And then we move on to a 3 good model using linear equations. Thereafter, we're going to go back to a 2 good model, but using non-linear equations. And finally, we end off this topic with an application in income determination. The position of equilibrium is very important to economists and applied in numerous models. Equilibrium, we know, is a point of rest, and all outside forces that alter a particular variable are constant. When these outside forces change, we will get a new equilibrium either instantaneously or otherwise. So we're going to work with a classic example of the demand-supply model. And we know in this model that demand is a function of price and supply is a function of price. A very important part now in this analysis is identifying endogenous versus exogenous variables, and more importantly, understanding the difference. So with an endogenous variable, we are referring to variables whose solution values we will obtain from our model. So in this example here, the equilibrium price and quantity are the endogenous variables. Exogenous variables are those whose values are assumed to be determined by forces external to the model. So, for example, the price of another good. If the price of another good were to change, this could change demand until a new equilibrium is reached. All right. And as we said at the start of this topic, we are focusing on partial equilibrium, and particularly in the first example that we are going to work through, where we look at an isolated market. So we're just looking at one good in that market, and we're going to look at identifying the equilibrium price as well as the equilibrium quantity. Now we need to remember that equilibrium is not necessarily desirable. In this topic in particular, we are simply looking at a position that is obtained. An economy can settle at an equilibrium position of high unemployment, which we would all agree is not a good thing. Now, in a later topic, you will look at something called goal equilibria, and you will work with optimization problems. Now, this is a completely different issue altogether from what we are going to be doing today. So in this later topic, you will look at things like maximizing utility, maximizing profit, or minimizing costs. In today's session, we are focusing on non-goal type of equilibrium. So we're just looking at that point of rest. So for example, we are going to be looking at equilibrium obtained by a market under given demand and supply conditions, and equilibrium of national income under given conditions of consumption and investment patterns. So now we're going to work through our first example, a partial equilibrium model, demand and supply, linear case. So we're working with linear equations. And we want to find the values of the endogenous variables that satisfy an equilibrium condition. All right, so we're working with demand and supply. As I said, it's a single good case, so this is an isolated market. And we know that in general, quantity is a function of price. More specifically, we can set out our mathematical model as follows. We have firstly our equilibrium condition here. We are wanting to identify equilibrium, and we know in equilibrium quantity demanded equals quantity supplied. Okay, there's no excess demand, there's no excess supply. These two are equal. All right, then we have our equation for quantity demanded, and it's equal to A minus BP. All right, so we can clearly see that quantity demanded is a function of price, and there's a negative relationship between the two. We know this, that as the price increases, for example, quantity demanded will decrease. Okay, and for quantity supplied, we also have our linear equation here, minus C plus dP, and again, quantity supplied is a function of price, and here there's a positive relationship between price and quantity supplied. In other words, as the price goes up, for example, the quantity supplied will also increase. All right, so these are the equations within our model, and we are going to use them in order to be able to identify equilibrium quantity and equilibrium price in this model. Now, A, B, C, D that we see here in these equations, these are referred to as parameters and effectively treated as given in the model, all right? But they're assigned a symbol and not a number or a numerical value, but they are given. In other words, they are not endogenous to our model. We have three endogenous variables that we are wanting to solve for: equilibrium price, equilibrium quantity demanded, and equilibrium quantity supplied. And we know that in equilibrium, quantity demanded equals quantity supplied. Just to point out as well, we indicate the equilibrium of these variables using an asterisk. On this slide, I've drawn something that's probably a little bit more familiar to you. There is a slight difference because what's represented here are the demand and supply curves, but you are normally used to seeing price on the y-axis and quantity on the x-axis. All right, but here we have followed mathematical convention where we put the independent variable, which is price, on the x-axis, and the dependent variables on the y-axis, which is quantity demanded, quantity supplied. All right, but otherwise this type of diagram should be quite familiar to everyone, because all we've done here is plot the demand graph and the supply graph. And we've worked with the equations that you saw on the previous slide for quantity demanded and quantity supplied. And what you really need to be able to do is to calculate the axis intercepts. And that's what I've done in these two boxes at the bottom here. So, for example, with the quantity demanded equation, the way to work out each intercept is to just for example, if you want to work out where the demand graph intercepts the quantity axis, you need to substitute 0 for where price is, because what you're trying to work out is when price is 0, what is quantity demanded. And this is what this little calculation enables you to do. And this is quite straightforward, because when price is naught, this whole term is naught, so quantity demanded is A. So in other words, when price is 0, quantity demanded is A. So that would be this y-axis intercept for the quantity demanded graph. And then to work out the x-axis intercept, you just change it around. So in other words, instead of substituting 0 in for P, you need to substitute it in for QD, because now you need to work out the intercept when quantity demanded is 0. We need to know the intercept on the x-axis. So if we substitute in 0 here and then solve for P, all right, then we work out that P is A over B. All right, so that would be this x-axis intercept for the demand curve. And then you could just connect those 2 points. And you would undertake the same exercise for quantity supplied, which I've set out here. And you know from first year that where these 2 curves intersect, that is equilibrium. Okay, so that would be the equilibrium price, and that would be the equilibrium quantity. So here we are identifying it graphically. All we want to do now in the next few exercises is to be able to identify this exact same point of equilibrium, but we're going to calculate it. We're going to do so using some algebra. We'll start our calculation by finding equilibrium price first. What you see here is the equations from the previous slide. And we know the equilibrium condition is, in equilibrium, quantity demanded equals quantity supplied. So in effect, in equilibrium, we can refer to both of these, well, we can refer to the equilibrium quantity. So we can restate these 2 equations. Instead of having QD and QS, we can have Q equals and Q equals, because we know that in equilibrium, quantity demanded and quantity supplied are equal to the same amount. And then what we can do is we can set these 2 equal to each other. So we've got A minus BP equals minus C plus DP. All right, so we have here a simultaneous equation, and we want to solve for P. And we'll start by taking minus C over to the other side. So we'll have A plus C on this side. Then we're going to take minus BP over to the right hand side, and we end up with this line here. And finally we factorize. We take out the common P. It's common to both of these terms, so we're left with P and then in brackets D plus B. And then we divide both the right hand side and the left hand side by D plus B, and we then are effectively solving for equilibrium price. This is the expression here, and this is a reduced form equation, which means that our endogenous variable price is expressed in terms of exogenous variables. And as we said on the previous slide, the parameters there are given and are effectively treated as exogenous variables. So here we have our reduced form equation, and we have our expression for equilibrium price. All right, so we note here that one of the endogenous variables has been expressed in terms of the parameters and not Q. So the other endogenous variable, okay, that's not here, right? And as I said, the parameters in a sense are behaving as exogenous variables. All right, so we've solved for P, but now we need to move on and solve for equilibrium quantity. So we've got our expression for equilibrium price, and we're going to use this in order to solve for equilibrium quantity. The way we do this is we either take the quantity supplied or quantity demanded equation and substitute in for P. All right, so here we've taken the equation for quantity demanded, which was A minus B P, and instead of saying P, we have substituted in the equilibrium, the expression for equilibrium price. All right, so we want to simplify this, and the way we're going to do it is we want to put both terms over a common denominator so that we can subtract the one from the other. So for this term here, A, remember the numerator is A, the denominator would be 1. So we have to find the lowest common denominator for 1 and then B plus D. So where we have 1 as the denominator here, the lowest common denominator for both of these terms is going to be the denominator of this term here. So here we've got B plus D as the common denominator, and now we've effectively multiplied 1 by B plus D. So what we do to the denominator, we have to do to the numerator, so we have to multiply A by B plus D. But this enables us to have both these terms, well, everything over a common denominator, and then we can simplify. So we multiply out this bracket, and we do the same for this bracket here, and we end up with this numerator here, and we can further simplify, and we end up with our expression for equilibrium quantity. And again, we're looking at a reduced form equation because here we only have parameters. So we've got our endogenous variable expressed solely in terms of the parameters, which we are taking as exogenous variables in this model. This example is very similar to the previous one, except now we are working with numbers. So we have a numerical example. So instead of A, B, C, D, the parameters in the previous example, we now have specific values. We have our numbers. But the approach is exactly the same. We still are dealing with one good, and we need to set quantity demanded and quantity supplied equal to each other in order to be able to calculate the equilibrium value for price first of all, and then quantity. So that's what's done here. 128 minus 9p equals minus 32 plus 7p. So we've set these two equal to each other, and now we just need to solve for p. All right, so taking 9p across to the right hand side, we will have 7 plus 9p, so we end up with 16p. And taking 32 across to the left hand side, we're going to have 128 plus 32, so that gives us 160, and we then calculate the equilibrium price of 10, and we can then substitute this value for price of 10 into either this equation up here or this one here. Instead of seeing p, you need to substitute in 10, and you will calculate an equilibrium quantity of 38. All right, and what's quite helpful is to then go back using our reduced form equations that we calculated in the previous example, and then substitute in the values for A, B, which remember is the quantity demanded parameters, A, B, and C and D comes from the quantity supplied equation, these parameters here, and you can substitute them in to these reduced form equations, and you will calculate the exact same answer. In this example, we extend our analysis slightly because we're now going to look at two goods, beef and pork, and we want to identify equilibrium such that both of the markets are in equilibrium simultaneously. So we've got here demand, supply for beef and demand supply for pork. And you are asked the question, are these goods complements or substitutes? So we have to look at the quantity demanded equation. And as we saw in the previous slide, the relationship between the price of beef and the quantity demanded of beef, it's negative. So as the price of beef increases, for example, quantity demanded of beef decreases. But if we look at the price of pork now, which has been entered into this equation, we see a positive sign. So that's telling us that as the price of pork increases, for example, then demand for beef will increase. So that indicates to us that these two would be substitute goods. And we see the same when we look at quantity demanded, the demand equation for pork, where we have the price of beef, positive sign telling us that as the price of beef increases, the demand for pork increases. All right, so we're looking at substitute goods here, and we are wanting simultaneous equilibrium in both of these markets. To solve this model, we're going to use the approach of substituting in variables. So we need to start with our two markets, and we are looking at equilibrium in each market, but across both markets at the same point in time. So here we've got beef, the quantity demanded beef, this equation here, and that we know in equilibrium will equal the quantity supplied of beef, and the same for pork. Okay, we can set quantity demanded equal to quantity supplied. All right, so we've taken the equations from the previous slide and simply set quantity demanded equal to quantity supplied in each market. All right, then for each of these now, we want to gather like terms and effectively simplify what we have. So if we just look at beef here, if we gather, we've got PB on this side, on the left-hand side, and PB on the right-hand side. So if we take minus 3 PB over to the right-hand side, we would have 15 plus 3 PB, and that would give us 18 PB, and that's what we see here. And then taking PP across, we would end up with minus PP. And then if we take our numerical values, if we gather them together all on the one side of the equation, so if we took our minus 5 across, we'd end up with 82 plus 5, which would give us 87. So this equation 1 here is the market for beef, where we've just gathered the terms with PB and PP, and we do the same with the market for pork, and we end up with this equation 2 here. All right, so we now have two equations, two unknowns, so we can go forward now and solve. And we're going to do so by substitution. And the way it's done so in this exercise, using equation 1, we isolate PP, okay, this variable. All right, so PP equals, and then taking all the other terms to the other side, we end up with this expression for PP equals 18 PB minus 87. So this we have from equation 1, the beef market, and we substitute in this expression for PP into this equation 2, which is the pork market. All right, so we have here minus 2 PB plus 36, but instead of writing PP, we use this expression here. Okay, so we substitute that in here, and then equals 98. All right, and then it's a bit of calculation, and we can calculate the equilibrium value for PB is 5. And then what we need to do is we have to take this and substitute this value back into equation 1, and we can solve for PP, which will give us 3. Okay, so we've effectively got now the equilibrium prices for beef and pork, and we can now go back to our initial equations and work out the equilibrium values for the demand for beef, all right, by either going back to the equation for the demand for beef or the supply of beef and substituting in PB or PP, and the same for pork. All right, and we can work out the equilibrium values for this market. Here is another example using a two-good model, shirts and jackets in this case, and you are encouraged to work through this example and confirm that you end up with the correct values for the variables in equilibrium. We extend the analysis further now by looking at a three-good model, and here we have good 1, good 2, and good 3, and we've got quantity demanded and quantity supplied for the three markets. So our starting point is to set all the equations quantity demanded equal to quantity supplied. For example, here if we take the first market, we set quantity demanded equal to quantity supplied, and then our next step is to gather like terms on the left hand side and set the equation equal to 0. So we've done that here for equation 1, and we'll do the same in market 2 and in market 3. So we end up with these three equations here, and there are three unknowns. There's P1 for good 1, P2 for good 2, and P3 for good 3. And we need to identify the set of prices, P1, P2, P3, that satisfies all of these three equations. So if we rewrite these three equations here, we are going to solve for the equilibrium values of P1, P2, and P3 using a process of elimination. And what we need to do is to choose one of the variables to eliminate. And here we are choosing P2. You could just as easily have chosen P1 or P3, but we're going to work with P2. And the next step is then to work with pairs of these equations in order to eliminate that variable. So here we've chosen the first pair of equation 1 and equation 3. So we're going to work with these two. And then the second pair in this example is equation 2 and equation 3. And again, we could just have easily have chosen equation 1 and 2 and worked with those together. All right, but let's work with the equations chosen in this example here, equation 1 and equation 3. And remember, we're going to eliminate P2. So we need the coefficients on these variables to be equal as a starter, the value of the number, and then we're either going to add or subtract these equations in order to eliminate that variable. So we need a 2 in front of this P2 here, and the way we will get that is by multiplying this equation through by 2. So 31 times 2 gives us 62, minus 11 times 2 gives us minus 22, 1 times 2 gives us 2, 1 times 2 equals 2. And we'll rename this equation now, or we'll name it equation 4. We'll number it equation 4. Now we're going to subtract equation 3 from equation 4. So we're going to do this here, and that's what you see on the next line. Here's equation 4, rewritten here, and we're subtracting from equation 4, equation 3. So we've written it out there. And remember now you need to multiply through by this minus sign. And in doing so, you will end up with this final equation here. Okay, 62 minus 24 gives you 38. Minus 22 and minus 1 gives you minus 23 P1. Plus 2 minus 2 gives you 0. So in effect, we've achieved what we wanted to achieve, which was to eliminate the variable P2. Plus 2 plus 7 gives us plus 9 P3 equals 0. Okay, so we now have this new equation here, which we are numbering equation 5. And we go through a similar process now with the next pairing that we've chosen, which is a pair 3 and 2. Okay, equation 3 and equation 2. And here, we now need to look at the value of P2 here. We've got minus 6 here and plus 2 here. We need these to be equal. So the easiest way to do that here would be to multiply equation 3 by 3. All right, and by doing that, we get these values here. So multiply all the terms in equation 3 by 3, and we end up with this equation here. And most importantly, we see that 2p2 times 3 gives us 6p2. And in the next step, what we're going to do is, having numbered this new equation, equation 6, we're going to add equation 2, there it is there, plus equation 6, okay? And we end up with this equation here, and most importantly, we see that we've got here minus 6p2 plus 6p2, so again, we have eliminated this variable here. And we end up with this equation number 7, and what we now have through this first step of the process of elimination, we have two equations with two unknown variables, P1 and P3. So we now have two equations, 5 and 7, with our two unknowns, P1 and P3. And our next step is to eliminate a further variable, and we're going to eliminate P3. You could have chosen P1. And the easiest way to eliminate P3 here, we need these coefficients to be equal. So we're going to times 9 by 19 and 19 by 9, and that's what we see happening here. So in other words, we multiply equation 5 by 19. So 38 times 19, 23 times 19, and 9 times 19, you get 171 equals 0. And then with equation 7, we multiply through by 9, and we end up with this equation here. And most importantly, we can see now that the numbers, the coefficient values for P3, these are the same, and we can add these two equations together. So we add this equation here, right, to this one here, and what we end up with is plus 171p3 minus 171p3, which is now eliminating p3, and we end up with an equation that only has p1. So minus 437p1 plus 36p1, but then if we take that over to the right hand side, we end up with 401p1, and 722 plus 882 gives us 1604. And then we simply divide through by 401, and we end up with the solution value P1 equals 4. We can then take P1 equal to 4 and substitute back in either to 5, equation 5, or 7. So we need to substitute in P1 equal 4 here or 4 here, whichever equation you choose to work with. Here, the solution is working with equation 5, and we calculate that P3 equals 6. So we now have the solution values for P1 and P3, and we can take these and substitute these back into equation 1, 2, or 3 that we saw earlier on in this example, and you'll be able to calculate that the solution value for P2 is 7. This slide contains another example using a 3-good model, and you need to use the same approach that we used in the previous example the process of elimination of variables in order to solve the system of equations. And you have here the equilibrium values, but of course the key thing is to see that you are able to get here and solve for P1, P2, and P3. Okay, so we're moving on to the next part of this topic, where we work with a non-linear equation. Up until now, we've worked only with linear functions, but here we're going to work with non-linear equations. And our example, our system of equations looks like this. So we're still dealing with demand and supply. So equilibrium is where quantity demanded equals quantity supplied. But if we look at the quantity demanded function, we can clearly see that it's non-linear. In fact, this here is a quadratic function here, and that is because the highest power that a term in the equation is raised to is the power of 2 or squared. So here we have here a non-linear function, and the supply function, this is still linear. All right, so our approach is the same as where we were only dealing with linear functions. We would need to set quantity demanded equal to quantity supplied, and that's what you see here. And then taking all these terms across to the right hand side and basically setting this equation equal to 0, and we end up with what we call our quadratic equation. And we need to just distinguish now between a quadratic equation, as we see here, and a quadratic function. A quadratic function, okay, which an example has been set out here. So the right-hand side is the same as our equation, but the left-hand side is quite different because we've got this here, f is a function of p. And with this quadratic function, we will have an infinite number of ordered pairs that satisfies this function here. So in other words, for any value of p, okay, we can substitute a value for p here, okay, for example, -6, and then if we substitute -6 in for p, then we see that the left-hand side, f as a function of p, would be equal to 7. If we substituted in -5 in the right-hand side, we would calculate 0, and that's another ordered pair. If we substituted in -4 for p, all right, we would end up with a value of -5. So this quadratic function, it specifies a rule of mapping from p to f of p, and all of these ordered pairs together plot the parabola. And a parabola, if you recall, is the graph that we plot with a quadratic function, and we'll see that on the next slide. So in other words, we have an infinite number of ordered pairs when we are working with a quadratic function. Now, with the quadratic equation, if you see, the right-hand side is the same. The difference comes in here, what we have written on the left-hand side, we have set this equal to 0. So we are looking for values for p that will basically set this equal to 0. And what we'll see in our example is we will calculate that there are in fact two values of p, or two values for p, that when we plug them into this equation, this here will equal to 0. Okay, so this is the quadratic equation, and we obtain this when we set the quadratic function equal to 0. And the important thing here is that the solution p-value, so these p-values that we calculate, or that effectively will end up with a value of 0 for this equation here, these solution p-values, these are the x-axis intercepts, okay, for our parabola, the graph, and we refer to them as the roots, and we also know them as our equilibrium values. And when solving the system of equations here, we are, remember, looking for the equilibrium price and the equilibrium quantity, okay, where this market is in equilibrium. And it's going to be one of these solution values, the solution P values, that will give us the equilibrium price. So here we see the parabola from the quadratic function that we saw in the previous slide. And if we took all the ordered pairs that we calculated using the quadratic function, some of which we saw on the previous slide, if you plotted all those points and then connected them, this is the shape of the graph that you would get, a parabola. And in this case, in this example, we can see that the solution P values, when we are working with the quadratic equation, okay, so when we've set this function here equal to 0, the solution P values, the P values that effectively set this equal to 0 are -5. So if you were to substitute -5 in for P here, you would calculate 0 and 1. So if you substituted 1 in for P, you'd also calculate 0 here. So these are the roots, okay, 1 minus 5. These are the solution P values. These are the x-axis intercepts. And as we'll go into a little bit more detail in the next slide, one of these will equal the equilibrium price in our market. Now what we see on this slide is the graph for the supply function, which remember is linear, and the graph of the demand function, which is nonlinear. It's a quadratic. So on this slide, the quantity supplied and quantity demand function have been plotted separately. To just distinguish this from what you see on the previous slide, remember on the previous slide, we were plotting the parabola for the quadratic function that we obtained when we set quantity demanded equal to quantity supplied. All right, so when we applied the equilibrium condition and we set quantity supplied 4p minus 1 equal to 4 minus p squared, then that, by taking all the terms over to the one side, then we would end up with the quadratic function that plots the parabola that you saw in the previous slide. So here we are plotting the quantity supplied and quantity demanded function separately. And of course, what's now useful is we can use a graphical approach to identify equilibrium, because remember, after all, that's what we are after. And you know, going back to first year, that the equilibrium is going to be at the intersection of the two curves. So that is indicated on this graph. So we can see, going back to what we saw on the previous slide, where we had the solution P values of 1 and -5, and I said to you, one of those is going to be the equilibrium price. And of course, straight away you should have thought, well, price is not going to be negative, and it follows therefore that the equilibrium price is 1. And indeed we can see that the equilibrium price in this market is 1, and we can also then calculate the equilibrium quantity, which would be equal to 3. All right, and also just to highlight, of course, now you would recall how to draw a straight line, and you may recall how to plot a parabola. Of course, the previous slide, there was a U shape. Here it's an inverted U, and we're not going to spend too much time on plotting the parabola at this point. We'll look at it more in the tutorial, but there is obviously an easy approach in order to be able to plot the parabola when you have a quadratic function. So in the previous slide, we identified equilibrium graphically. Now we're going to calculate the solution values. So we are going to do so using our quadratic formula. And you can use this when you have a quadratic equation. If you think of the quadratic equation in a general form, ax squared plus bx plus c equals 0, then we can use the quadratic formula in order to calculate the solution values for x in this case. So in our example, we have our quadratic equation where we're obviously trying to calculate solution values for p, and a would be the coefficient on p squared, so it's 1, all right. B would be the coefficient on p, so it's plus 4, and c is this final term here, which is minus 5. Okay, we need to remember to take the appropriate sign with the value. All right, then we just need to substitute into our quadratic formula here. So the formula is minus b plus or minus b squared minus 4ac, all in bracket raised to the power of a half. Or you can think of what's in the bracket, you would need to find the square root. Okay, and then in the denominator, you've got 2 times a. So wherever you see the b, you substitute in for b. Wherever you see the a, you substitute in your value for a. And wherever you see the c, you substitute in your value for c. And that's what's been set out in this line here. And then working through the calculations, you get to this point here where we've got minus 4 plus or minus 6. Okay, 6 is what we calculate working with this bracket here, this calculation here. And then in the denominator, we've got 2, because obviously the denominator is 2a, and a in our example is 1. All right, so this now is where we get the 2 solution values. So if we think first of all of minus 4 plus 6, you're going to end up with plus 2 over 2, so 2 over 2. And when we work with minus 4 minus 6, we end up with minus 10 over 2. So we've got these 2 solution values, which we've seen on the previous slides. So we've got 1 and minus 5 when we simplify these. And as I said previously, we are only interested in positive values of p. So we take the solution value of p equals 1. This is our equilibrium price. And if we substitute that back into our original equations, then we will get the solution value for Q, for quantity, which is 3. All right, and there we have solved this system of equations where we are working with a nonlinear function in one of the cases. All right, and just to note that if we have a higher polynomial, okay, such as a cubic function or something even higher, then the approach is the same, okay, the principle is the same, but the factoring becomes a little bit more complicated. So actually identifying the solution values becomes a little bit more complicated, but the approach would be the same, although we don't go into this in detail in this particular module. So here's another example which you can work through. All right, you've got quantity demanded, which is nonlinear, quantity supplied, which is linear, and you've been asked to solve the equilibrium values for P and Q. So you're going to be taking the exact same approach that we took in the previous example. And obviously the important thing is to see that you are able to get to the solution. So I've put the solution here for you to see. But what's more important than that is making sure that you get there so that your method is correct. Here we have another example where we have quantity demanded and quantity supplied in a market, and we will want to solve for the equilibrium values of P and Q. So the approach we take is going to be very similar, but these two equations will maybe look a little bit different to you because of the way that they've been presented here. But in essence, they are still showing a relationship between price and quantity, and also for quantity supplied, price and quantity, which is obviously at the heart of quantity supplied and quantity demanded. So the best approach to take with this type of example is to actually eliminate the variable P as a starting point, because then you are left with an equation that's solely in terms of Q. It will be a quadratic equation, so you'll use your quadratic formula to solve for Q, but then obviously once you have Q, you can go back and solve for P. So we'll take a look at this approach on the next slide. So this slide contains the workings, and I've rewritten the two equations up here in this blue box. And remember, we want to eliminate the variable P, so we want the coefficient on the P variables to be the same so that we can then either add or subtract the equations in order to eliminate the P. So what we're going to do here, we've got 3P here, we've got 1P here. So we will multiply this quantity supplied equation, which is equation 2, we'll multiply it by 3. So that's what you see here. So we end up with 3P minus 6Q squared plus 3 times 3 is 9, plus 71 times 3 will give you 213. All right, and now what we can do is we can subtract this new equation here, which we've numbered equation 3, from equation 1. So we would go equation 1 minus equation 3, okay, similar to how you saw on the previous slide when we looked at the elimination method in detail. And you will end up with this equation here, which you can work out for yourself. And the most important point at this stage is that we have eliminated the P variable. So we have our equation solely in terms of Q. We have a quadratic, and we can solve it now using the quadratic formula. So the key thing now, of course, is to identify A, B, and C. So A will be plus 7, B will be minus 4, and C will be minus 315. All right, and then we will substitute into the quadratic formula, which I haven't restated here in terms of A, B, and C. I've just substituted in. But something I want to point out, for example, if you recall, the formula is, it starts with minus B plus or minus B squared minus 4AC all over 2A. And here, if you had forgotten to include the minus sign as in your B here is minus 4, you would have this term here at the front wrong, okay, because it's minus B, so substituting minus 4 in for minus B, obviously the minus and the minus will become positive, and that's what you see here. So you need to be very careful about that, because if you get your signs wrong, you're going to end up with the wrong answers. All right, and the same here. You can see it's minus, C here is minus 315. All right, and then it's just a case of calculating correctly, and you end up at this point here. You will have two solution values for Q, 7 and minus 6.42, but as with price, we're not thinking in terms of negative quantities, so our solution value, our equilibrium value for quantity will be 7, and if we then go back to our original equations, 1 and 2, you can use either one and substitute in for Q, right, so up here, then you'll be able to calculate the equilibrium price as well, which in this case is 6. All right, and here's another example for you to go through and work through on your own using the similar approach that we've just used. And again, you have the solution values, but as I said previously, the most important thing is, or the more important thing at this point, is to see that you can get there. All right, that you can get to these answers. So here we move on to the last part of this topic, our application and income determination. And up until now, we've focused on microeconomics, where we've looked at quantity demanded and quantity supplied in a given market. But there are also nice examples of equilibrium analysis in macroeconomics too. And we're going to have a look at that at one of these here with the Keynesian national income model. So we've got quite a simple model here. We've got y equals c plus I plus g. This, if you recall from macroeconomics, would be our equilibrium condition, where national income y must be equal to total planned expenditure. And we can see in this particular model, expenditure consists of consumption spending, investment spending, and government spending. And then what we also are given is a consumption function, all right, where we've got A, which would be autonomous consumption, and B, our marginal propensity to consume. And we know that consumption spending is a function of income. So our starting point, let's see which variables are endogenous and exogenous. So the endogenous variables, those are the ones whose values we are wanting to obtain from our model. And in this case, we have our consumption function. So we would be able to work out consumption within this model here, and also income. Okay, we would want to obtain from the model. If we look at A and B, these are our parameters. So these would be exogenous. All right, so looking at this box down here, we've got C and Y as our endogenous variables, and our exogenous ones, A and B, our parameters. And then investment spending and government spending. Clearly, we don't have a function for these here, so we can see that we will be treating these as autonomous or exogenous in this particular model. All right, so we need expressions. We're going to end up with expressions for the equilibrium values of y and c, and these are going to be expressed in terms of the exogenous variables. So in other words, we are looking at the reduced form here, as we did in our very first example, where we looked at quantity demanded and quantity supplied at the beginning of this topic. All right, and to solve now for equilibrium, the easiest way to start is by substituting consumption into income. Okay, so we've got y equals c plus I plus g, and instead of having c here, we will substitute in the consumption function in for c, and we end up with what you see here. And then we have our equation. There's just one unknown now. We've got it all in terms of y, and we can now solve for y. So if we took this term to the other side, we'd have y minus by, and factorizing, so taking out the common y, we'd end up with, in brackets, 1 minus b times y, and then a plus I plus g all on the right hand side, and then just divide through by what's in the bracket, 1 minus b, divide the left hand side and the right hand side, and we end up with this solution, or this expression here. And you can simplify this further, where you can change the way it's presented as follows. You'd have 1 over 1 minus b, and then have a plus I plus g all in brackets here. And this might be a little bit more familiar to you in terms of what you've seen in macroeconomics. Remember, equilibrium income is the multiplier times by the components of autonomous expenditure. So here you've got autonomous consumption, investment spending, and government spending. And then this would be 1 over 1 minus the marginal propensity to consume, which you know is the multiplier. All right, so this is our expression for equilibrium income, and now we want to find the expression for consumption. All right, so now that we've got equilibrium income, we can take this and substitute it into the consumption function. So here we have our consumption function, and we want an expression for consumption at equilibrium, and that obviously depends on equilibrium income, so we'll substitute in our expression for equilibrium income here. So instead of y, all right, we've substituted in for y. All right, and then it's just simplifying all of this, and what's been done in this example, we've removed, or we've multiplied through by 1 minus b, and that effectively takes 1 minus b out of the denominator of this term, but we need to multiply c by 1 minus b, multiply a by 1 minus b, and then obviously by multiplying this term by 1 minus b, what's in the denominator will cancel with that 1 minus b. All right, and then we just want to multiply through the brackets, all right, and simplify accordingly, and then we end up with this line here. And to isolate c, we're now going to divide through by 1 minus b, and we end up with this expression here for consumption. All right, so we now have our endogenous variables, y and c, expressed in terms of the exogenous variables only, so these are in the reduced form. This here and this here. So here we have another macroeconomic example, a Keynesian model, similar to the previous one. Here would be our equilibrium condition. An equilibrium income equals consumption spending plus investment spending. All right. This example is a little bit different because instead of the parameters that we had in the consumption function, we now have numerical values. We now have numbers. All right. And we also are now working with taxes. So we have to calculate disposable income, which we should recall from macroeconomics is income minus taxes. Okay, so you're asked to identify exogenous and endogenous variables and then find equilibrium income with and without tax. So if we think of question 1, first of all, if we have a look at what we have in this model, if we take a look, T and I, so this would be autonomous taxes because these are given, all right, and investment spending is given. So we would clearly be treating investment and tax as exogenous. If we look here at this function here, income, we would want to calculate from the model, all right, so that would be endogenous. Similarly, with disposable income, we'd want to calculate that within this model. It's not given, we need to calculate it once we know what national income is. Consumption spending as well, we will calculate that within our model. So in terms of endogenous variables, that would be C, YD, and Y. All right. So here we have our endogenous and exogenous variables just set out in this box. And now we need to answer question 2. And we are after equilibrium income. We've been asked to solve for equilibrium income, assuming that there's no tax, and then assuming that there is tax. So the only difference now is, of course, when there's no tax, then T effectively would be equal to 0. Okay, so we're going to solve first of all assuming that T is 0, and we've got our equilibrium condition, which is y equals c plus I, and as we did with the previous example, we're going to substitute in the consumption function here. So the consumption function, if we go up to this red box, is 100 plus 0.6 yd, But now, because we are assuming taxes are 0, YD, disposable income, will be equal to national income. Okay, because we're assuming there are no taxes in this model. All right, so for the consumption function now, we could actually write 100 plus 0.6y, and that's what you see here. And then for investment spending, it's given as 40, and we substitute in 40, and then it's a straightforward calculation. Take the y term across to the other side, so we gather the y terms, so we'll end up with y minus 0.6y equals 100 plus 40. This will be 0.4y equals 140, and in equilibrium, national income would be equal to 350, and this is assuming that there is no tax. So if we now assume that there is tax, we are working with t equals 50. That's been given to us, so t is no longer equal to 0. So it's the same approach, except now, of course, the consumption function, where we've got yd, it's going to be y minus 50. Okay, we are no longer assuming that yd is equal to y, okay, because we are saying that there are now taxes in the model. So that's the main difference now, but we're going to substitute in the consumption function here. So it'll be 100 plus 0.6 y minus t, all right, plus 40, which is investment spending. And here in this next line, we've just added the 100 plus the 40, so you've got 140 plus 0.6 y minus t. Okay, so there's the difference here. Taxes are in this model, so we have to substitute in, but then the approach is the same. It's just calculating through, so we would multiply through this bracket by 0.6, okay, and then gather the y terms on the left hand side, and through a little bit of calculation you would be able to calculate that equilibrium income when there are taxes is 275. Okay, and that would certainly be in line with expectations, because we know that taxes will have a dampening effect on expenditure and hence on income. Okay, so income in this model, equilibrium income, is lower than when there are no taxes. All right, so here we have one last example, which I'm going to leave to all of you to work through. But I will give you a few pointers in terms of getting you started. So you have now, it's a macroeconomic example. It's a bit different from the previous two, because the previous two focused on the commodities market, the goods market. But here you can see there's also the money market, all right, which you know is another market in the macroeconomy. And you've been asked to find the values of y and little I, the interest rate, when both the commodity markets and money markets in equilibrium. So you need to start with each market separately and calculate the equilibrium equation. So here we've got y equals c plus I, which we know is the equilibrium condition in the commodities market. And you would want to substitute in for consumption. Here's the consumption function, substitute in. And we also have here a function for investment spending, all right? And once you substitute in for C and for capital I, investment spending, you'll end up with an equilibrium equation for the commodities market, which is only in terms of y and little I, okay, the interest rate. Then for the money market, again, you want an equation for equilibrium. And we know that equilibrium is where money supply equals money demanded. We've got two components to money demand here. So we have to set money supply equal to total money demand. All right. And again, you'll end up with an equilibrium equation solely in terms of y and little I. So you'll end up with equilibrium equations for each of these markets. So you'll have two equations and you'll have two unknowns. You'll have y and little I. And then you will use those two equations. You will solve simultaneously and you'll be able to calculate the values that you are requested to calculate. And I have given you the solution values here, but as with the previous examples, at this point, it's more important that you can actually get there and that your method is correct rather than what the value is at this point. You obviously want to get the right answer, but you need to, at this point, be ensuring that your method and your calculations are correct.